Welcome to this life cycle assessment course for companies. I hope this course meets your expectations and provides you with a solid introduction and practical guidance for your LCA journey. If you have any questions, need further training, or would like additional support, please feel free to reach out to me via my social media channels, available on my website, sergiarfelis.com. Let's get started. Today, we will cover several key topics. First, we'll begin with an introduction to life cycle assessment, giving you an overview of the fundamentals. Next, we'll discuss why companies need LCA and the value it brings to businesses like yours. We'll then look at the LCA framework and standards, focusing on ISO 14040 and 14044. After that, we'll move into a practical workshop and case study, where we'll explore these standards in action and work through each stage of an LCA. This includes Phase 1, Goal and Scope Definition, Phase 2, Lifecycle Inventory or LCI, Phase 3, Lifecycle Impact Assessment or LCIA, and Phase 4, Interpretation. We'll also discuss practical applications of LCA in business, followed by an overview of available LCA tools and resources. Then, we'll talk about how to overcome common challenges in the LCA process. Finally, we'll wrap up the session with a summary and key takeaways. Are you ready to get started? Who knows what LCA is? Are you sure? We call LCA to the methodology for evaluating the potential environmental impacts of a product, process, or service throughout its entire life cycle, from raw material extraction, production, and distribution, through use, to end-of-life treatment such as recycling or disposal. This is referred often as cradle-to-grave, as you can see on the image in the right, emphasizing the holistic focus on the overall life cycle rather than impacts on any one facility, user, or stakeholder. If recycling and reuse of materials is included in an LCA analysis, the techniques may also be termed cradle-to-cradle, implying a continuous production loop or circular economy. Within organizations, the boundaries selected are usually cradle-to-gate, from extraction of raw materials to the point the product leaves the factory, excluding its use and disposal phases. Let's consider a manufactured product's life cycle. It typically involves stages like raw material extraction, processing, transportation, product manufacturing, transporting the finished product to where it's used, the actual use phase, and finally disposal or recycling. The scope of life cycle assessment ensures analysts measure environmental impacts across this entire chain without double-counting emissions at each stage. It also prevents shifting burdens. For example, reducing energy use in one stage might unintentionally increase pollution elsewhere. By analyzing the full life cycle, LCA captures these hidden trade-offs, giving a complete picture of a product's true environmental footprint. Life cycle assessment techniques can be used to evaluate environmental impacts in many different categories. One common way is to measure cumulative energy demand, which is the total energy used throughout a product's life cycle. Another important approach is to look at emissions. Emissions are often summarized using standardized metrics that reflect the specific pollutants released. For example, global warming potential, or GWP, is driven by greenhouse gas emissions. Eutrophication refers to the over-enrichment of water with nutrients, often from agricultural runoff. Other impact categories include acidification of water and soil, ozone layer depletion, and different types of ecotoxicity. LCA can also help us understand the depletion of important resources, such as fossil fuels, water, and critical minerals. But which of these impact categories is the most important? The answer depends on your product, your industry, and your goals. For some products, global warming potential might be the main concern. For others, resource depletion or water use could be more critical. The best approach is to consider the context of your study, follow relevant regulations, and consult with stakeholders to decide which impact categories to prioritize. This helps ensure you are focusing on the most meaningful environmental issues for your specific situation. On this slide, you see three major environmental challenges that are important for companies to understand when using life cycle assessment. These challenges are eutrophication, climate change, and ozone depletion. Starting on the left, the image of a river with algae blooms represents eutrophication. Eutrophication happens when too many nutrients, such as nitrogen and phosphorus from agriculture or industry, enter water systems. For companies, this can result from fertilizer use or wastewater discharge. LCA allows businesses to measure and manage these nutrient emissions across their supply chain, helping to reduce environmental risks and meet regulations. In the center, the image shows temperature changes over the past 50 years. This highlights climate change, which is mainly caused by greenhouse gas emissions from activities like energy use, manufacturing, and transportation. Through LCA, companies can calculate the carbon footprint of their products and processes. This information is essential for meeting climate regulations, improving energy efficiency, and responding to customer and stakeholder expectations for climate action. On the right, the image of the ozone hole represents ozone depletion. This issue is mainly caused by chemicals such as CFCs, which were used in refrigeration and manufacturing. Although many of these substances are now regulated, LCA helps companies assess the impact of chemicals used in their products and avoid substances that can harm the ozone layer. By using LCA, companies can identify and address these environmental impacts, reduce regulatory risks, improve resource efficiency, and strengthen their reputation for sustainability. Let's talk about two main approaches in life cycle assessment, or LCA: Attributional LCA and Consequential LCA. Understanding the difference between them is important for companies making decisions about sustainability. In an attributional LCA, the goal is to measure the total environmental impact that can be assigned to a specific product or service. This approach looks at the entire life cycle of the product as it exists today, using average data from the current supply chain. It helps answer questions like, what is the current environmental footprint of this product? Attributional LCA is useful for reporting, benchmarking, and understanding the present situation of your company's operations. On the other hand, a consequential LCA is focused on what happens if you make a change, such as launching a new product or increasing production. This approach models the environmental impacts that result from a specific decision or change in demand. It considers how the market and supply chain might respond, and what the broader consequences would be. Consequential LCA answers questions like, if we change this process, what will be the environmental impact? It is especially helpful for decision-making, policy analysis, and evaluating the effects of business changes. To summarize, Attributional LCA looks at the current situation and assigns impacts to products as they are today. Consequential LCA looks at possible changes and predicts the impacts of business decisions. Choosing the right approach depends on your company's goals, whether you want to understand your existing footprint or evaluate the consequences of future changes. Why companies need LCA? LCA is a valuable tool that helps companies manage their environmental responsibilities and improve business performance. LCA enables companies to identify environmental hotspots and focus on improvements that matter most. It helps you make informed decisions about which raw materials to use and which suppliers to choose, so you can optimize resource use, cut waste, and improve energy efficiency. LCA also provides the data you need for ESG reporting, allowing you to communicate your progress transparently to investors, customers, and regulators, and to build trust with all stakeholders. CA is also important for navigating regulations and compliance. For example, regulations like the EU Corporate Sustainability Reporting Directive require companies to report detailed environmental impacts across their value chains. LCA supplies the data needed for compliance, covering climate change, pollution, biodiversity, and resource use. In Europe, new requirements like digital product passports will need lifecycle data for products sold in the market, and using LCA prepares your company for evolving standards such as ISO 14040, ISO 14044, and the GHG protocol. There are also real business benefits to using LCA. By identifying inefficiencies, LCA helps companies cut unnecessary resource use, reduce energy consumption, and minimize waste. It supports eco-design, making it easier to develop products that use less material, are easier to recycle, or have lower carbon footprints. Verified LCA data also makes it easier to achieve eco-labels and win contracts with eco-conscious customers. LCA helps you select suppliers and logistics options with lower environmental impacts, and it supports continuous improvement by creating a feedback loop for ongoing sustainability and operational excellence. As we have been already mentioning, main standards in the LCA field are ISO 14040 and ISO 14044. These standards help companies measure and manage the environmental impacts of their products, processes, or services from raw material extraction all the way to disposal. ISO 14040 explains the basic principles and the overall framework for doing an LCA. It describes the four main steps. First, defining the goal and scope of your study. Second, collecting data in what is called the lifecycle inventory. Third, assessing the environmental impacts. And finally, interpreting the results to draw conclusions. ISO 14044 builds on ISO 14040 by giving more detailed instructions for each step. It tells you how to set clear goals, collect and manage data, choose impact categories, and interpret your findings. It also covers how to report your results and have them reviewed for accuracy and credibility. Following ISO 14040 and ISO 14044 makes sure your LCA is consistent, transparent, and trusted by customers, regulators, and other stakeholders. These standards help companies meet legal requirements, improve their processes, and show their commitment to sustainability. Let's explore now the 4 main stages of LCA, using practical examples to show how each stage works in real business situations. Goal and scope definition. In this first stage, you decide what you want to study and why. For example, a company might want to measure the carbon footprint of a new office building designed for 1,000 people over a 60-year lifespan. Here, the company defines what part of the building's life cycle to include, such as raw material extraction, manufacturing, construction, use, and end-of-life disposal, and what to leave out, like impacts from public utilities not directly tied to the building. Life cycle inventory. Next, you collect data on everything that goes in and out of the system you've defined. In the office building example, this means gathering details about all the materials used, like 5,000 tons of concrete, 2,000 tons of steel, and the energy required both for construction and operation. You also track outputs, such as emissions and waste. For instance, the construction phase might generate 3,500 tons of carbon dioxide equivalent emissions. Life cycle impact assessment. In this stage, you evaluate the environmental impacts based on the data collected. For the building, you would look at how much the materials and energy use contribute to climate change, resource depletion, or water pollution. For example, you might find that using cross-laminated timber instead of concrete reduces the building's carbon footprint, or that certain HVAC systems lower operational emissions. Interpretation. Finally, you analyze the results to draw conclusions and make recommendations. In our building example, the company might discover that most emissions come from the production of steel and concrete, so they could focus on sourcing recycled materials or switching to lower-impact alternatives. The interpretation phase helps decision-makers understand where the biggest environmental impacts are and what actions will have the most benefit. By following these 4 stages, companies can identify environmental hotspots, compare alternatives, and make informed decisions that lead to more sustainable products and operations. Let's look at an example. Imagine a company called Plastic Producer. This company manufactures polypropylene pellets that contain 30% post-consumer recycled material. These pellets are used in automotive parts, packaging, and consumer goods. On this slide, we define the goal of our LCA, to evaluate the environmental impacts of producing 1 ton of recycled polypropylene with 30% post-consumer recycled content. The purpose is to validate sustainability claims, identify opportunities for improvement, and support customer decision-making. We also define the functional unit, which is 1 ton of recycled polypropylene pellets ready for use. This will be the basis for all our calculations. At this stage of the LCA, we also decide where we will collect data and which impact categories we are interested in studying. We continue by setting the system boundaries, which will be cradle-to-gate with cutoff approach, and we will define which stages are included in our calculations. Those are collection, sorting and washing, reprocessing or extrusion, and packaging. When performing a life cycle assessment, or LCA, it is important to decide how to set the system boundaries, especially when dealing with recycled materials or products with multiple life cycles. Here are 3 main approaches. The cutoff approach, sometimes called the 100:0 method, assigns all the environmental impacts of producing a material to the product that uses it for the first time. If the product is recycled, the next user does not inherit any of the original production impacts. Instead, they only account for the impacts of the recycling process itself. This approach is simple and avoids carrying environmental burdens into future product cycles, but it does not reward the use of recycled materials in new products. The substitution approach, also known as the 0:100 or avoided burden method, works differently. Here, the first product is credited, or given a benefit, for the potential recycling at the end of its life. This credit corresponds to the potential avoided primary materials of recycling. The next product made from the recycled material takes on all the environmental impacts as if it were made from new material. This approach is useful for highlighting the environmental benefits of recycling, but it can be complex to apply because it requires assumptions about what the recycled material is replacing in the market. The 50:50 approach, used in the product environmental footprint or PEF method, splits the environmental impacts equally between the first and the second life of the material. In this method, half of the impacts from producing the material are assigned to the original product, and the other half go to the product that uses the recycled material. The PEF method may also adjust for the quality of recycled materials and market demand, making it a compromise between the cutoff and substitution methods. This approach is designed to support a circular economy by fairly sharing the burdens and benefits of recycling. After collecting all the data, our inventory table looks like this. Let's introduce here two fundamental concepts in research and data analysis: primary and secondary data. First, what is primary data? Primary data refers to information that is collected directly from original sources. This means the data is gathered first-hand by the researcher for a specific purpose or project. Examples of primary data include surveys, interviews, experiments, and direct observations. For instance, if you conduct a survey to understand people's opinions on recycling, the responses you collect are primary data. The main advantage of primary data is its relevance and accuracy for your specific research question. However, collecting primary data can be time-consuming and expensive. Now, let's move on to secondary data. Secondary data is information that has already been collected by someone else, often for a different purpose. This data is usually available through reports, publications, databases, or official statistics. For example, if you use government statistics on plastic waste or refer to published scientific articles for your research, you are using secondary data. The main benefit of secondary data is that it is often easier and faster to access, and it can provide valuable context or background information. However, it may not be tailored to your exact needs, and you need to assess its quality and relevance carefully. In summary, primary data is original and collected directly by the researcher, while secondary data is pre-existing information gathered by others. Both types of data are important, and choosing between them depends on your research goals, resources, and the level of detail you need. Let's discuss Phase 3 of the Life Cycle Assessment, known as Life Cycle Impact Assessment, or LCIA. In this phase, we take the life cycle inventory data and convert it into quantifiable environmental impacts. This is done using standardized methods such as recipe, CML, or the environmental footprint method. Our goal here is to evaluate the environmental performance of the product. To do this, we rely on specialized LCA tools like Simapro, Sphera, openLCA, and databases such as EcoInvent. These tools use environmental factors to translate our collected activity data into results for a range of environmental impact categories, following the chosen LCA methodology. For each category, we will obtain a specific result. The categories include climate change, ozone depletion, human toxicity for both cancer and non-cancer effects, particulate matter, ionizing radiation, photochemical ozone formation, and acidification. We also assess eutrophication in terrestrial, freshwater, and marine environments, ecotoxicity in freshwater, land, and water use, as well as resource use for both fossil and mineral resources. A key question at this stage is, what should we prioritize? With so many impact categories, it's important to focus on those most relevant to our case study and stakeholders. This ensures our assessment leads to meaningful environmental improvements and supports informed decision-making. We will see in next slides how can we be sure about what are the categories on which we are impacting more. Let's explore Phase 4 of the Life Cycle Assessment, Interpretation. In this final phase, we systematically review the results from the inventory analysis and impact assessment. The main objective is to draw reliable conclusions, identify key issues, and provide recommendations for improvement. This ensures that our findings are robust, consistent, and aligned with the original goal and scope of the study. Interpretation involves several important steps. Hotspot analysis, where we pinpoint the stages or processes with the highest environmental impacts. Normalization, which helps us understand the relative importance of different impact categories. Weighting, to prioritize impacts according to their significance. Uncertainty checks, to evaluate the reliability of our results. And sensitivity analysis, which tests how changes in assumptions or data affect the outcomes. By following these steps, we make sure our LCA results are meaningful, transparent, and actionable for decision-making. Hotspot analysis is a powerful tool used in life cycle assessment to identify the stages, processes, or materials within a product's life cycle that contribute most significantly to its overall environmental impact. By focusing on these high-impact areas, such as carbon emissions, water use, or waste generation, Hotspot analysis helps organizations prioritize their sustainability efforts and allocate resources efficiently. This approach ensures that attention is given to the most relevant life cycle stages and actors, whether that's raw material acquisition, manufacturing, or end-of-life management. The main benefit of hotspot analysis is that it streamlines decision-making by highlighting where interventions will have the greatest effect, and it also helps stakeholders understand potential trade-offs between different sustainability priorities. For example, it can reveal if a single process dominates multiple impact categories, or if different emission sources are responsible for different environmental issues. But what happens if different emission sources impact different midpoint indicators? This is where the analysis becomes more nuanced, requiring a multi-indicator perspective to ensure that sustainability strategies address all significant hotspots across the product's lifecycle. Normalization and weighting will help us identifying the most critical indicators in our case. Normalization is a key step in lifecycle assessment that helps put environmental impacts into perspective. By comparing LCA results to a reference system, such as the average annual footprint of a person, a region, or the entire world, we can better understand the relative importance of each impact. This process makes it easier to interpret and communicate results, as it translates technical values like kilograms of carbon dioxide equivalent into more relatable terms. For example, if a product emits 600 kilograms of CO2 equivalent and the average annual footprint for an EU citizen is 8,400 kilograms, the normalized impact is 0.071. This means the product's emissions represent 7.1% of what an average EU citizen emits in a year. On the other hand, we have weighting. Weighting is a crucial step in life cycle assessment that assigns relative importance to different impact categories based on stakeholder values or policy priorities. This process helps translate technical results into actionable insights by reflecting which environmental issues matter most in a given context. There are several methods for weighting. Distance to target. This method gives higher priority to impact categories that are furthest from meeting sustainability goals, such as planetary boundaries. Panel-based. Here, expert or stakeholder surveys are used to determine societal preferences for each impact, as seen in methods like recipe. Monetary valuation. This approach assigns economic values to impacts, such as applying carbon pricing to greenhouse gas emissions. The EF 3.1 LCA method, as proposed by the European Commission, combines normalization and weighting to support decision-making. On the right, you can see an example table listing impact categories alongside their normalization and weighting factors. For instance, climate change receives a weighting factor of 21.1%, indicating its high perceived importance compared to other categories like freshwater ecotoxicity or land use. By applying these weighting factors, we can prioritize actions and communicate results more effectively to stakeholders, ensuring that LCA outcomes are aligned with societal and policy objectives. Uncertainty checks are an essential part of life cycle assessment, ensuring that the results are robust and reliable for decision-making. Uncertainty in LCA can arise from various sources, including data quality, modeling assumptions, scenario choices, and even subjective value judgments. To address these uncertainties, several approaches are commonly used. Identification and prioritization. The first step is to identify the main sources of uncertainty, such as parameter uncertainty from data variability, model uncertainty from methodological choices, and scenario uncertainty from future projections. Prioritizing these sources helps focus efforts on the most influential factors. Quantitative methods. MonteCarlo simulation is a widely adopted technique in LCA software like Simapro. It involves repeatedly running the LCA model with randomly varied input parameters, based on their probability distributions, to generate a spread of possible outcomes. This provides a statistical range and confidence intervals for the results, making the uncertainty explicit. Sensitivity analysis. This method systematically varies key input parameters or assumptions to assess how much they influence the final results. Sensitivity analysis can be local, screening, or global, and helps identify which variables have the greatest impact on uncertainty. Tools such as tornado charts or spider plots are often used to visualize these effects. Use of probability distributions. Instead of relying on single-point estimates, uncertainty analysis often employs probability distributions for input data, reflecting the range and likelihood of possible values. This approach allows for more nuanced and informative results. By conducting uncertainty checks, LCA practitioners can communicate not only the best estimates of environmental impacts but also the confidence and reliability of these results. This transparency supports better-informed decisions and highlights where further data collection or methodological refinement may be needed. Life cycle assessment, or LCA, offers a wide range of practical applications for businesses across different sectors. Let's look at some of the most impactful ways LCA is used in real-world business contexts. Product design and eco-innovation. LCA helps identify environmental hotspots throughout a product's lifecycle, guiding better material selection and design for recyclability. For example, companies can redesign packaging to reduce both the carbon footprint and material use, resulting in more sustainable products. Supply chain optimization. By assessing and comparing suppliers based on their life cycle impacts, businesses can make informed decisions to lower their overall environmental footprint. This might involve choosing raw materials with lower impacts or sourcing from local suppliers to cut emissions. Marketing and sustainability claims. LCA provides robust, ISO-compliant data to substantiate green marketing claims. This is essential for achieving eco-labels such as EPD or Blue Angel, which help differentiate products in the marketplace and build consumer trust. Regulatory compliance and reporting. With increasing regulatory demands, LCA supports compliance with frameworks like the CSRD, EU Product Environmental Footprint, and Digital Product Passports. Transparent LCA data is also valuable for tenders and public procurement, ensuring businesses meet legal and market requirements. Cost reduction and efficiency. LCA reveals opportunities to save energy, water, and materials, leading to both environmental and financial benefits. Process improvements identified through LCA can lower operational costs while reducing environmental impacts. Risk management and stakeholder engagement. Finally, LCA helps businesses anticipate regulatory changes and respond to customer or investor sustainability expectations. Results from LCA can be integrated into ESG reports and stakeholder communications, supporting proactive risk management and stronger stakeholder relationships. In summary, LCA is a versatile tool that drives innovation, operational efficiency, compliance, and credibility, making it a cornerstone of modern sustainable business strategy. When comparing the leading LCA tools, Simapro, openLCA, and GaBi, each offers distinct advantages tailored to different user needs and budgets. Simapro is a commercial tool positioned at a mid to high price point. It provides access to a wide range of databases, including EcoInvent, AgriFootprint, LCIA, and various proprietary sources. Its main strengths are a user-friendly interface, robust scenario analysis capabilities, and customizable reports. Simapro also integrates well with Excel, making it intuitive for users familiar with spreadsheet-based workflows. openLCA stands out for its open-source flexibility and cost-effectiveness. While the core software is free, premium databases may incur additional costs. openLCA supports multiple databases such as EcoInvent, ELCD, and AgriBalise through plugins. Its key features include open-source adaptability, regionalized LCIA, and developer tools via an API. However, its user interface is more functional than polished, requiring a higher level of technical skill compared to Simapro. GaBi, developed by Sphera, is a high-cost commercial solution known for its advanced modeling capabilities, especially for complex systems. It offers access to extensive proprietary and industry-specific databases, including GaBi and EcoInvent. GaBi's advanced features include iReport for reporting and integration with lifecycle costing, LCC, and lifecycle working environment, LCWE, analysis. Its graphical user interface is the most advanced among the three, but it comes with a steep learning curve. In summary, Simapro is favored in academic settings for its balance of usability and features, openLCA appeals to those seeking flexibility and lower costs, and GaBi is preferred for advanced industrial applications requiring comprehensive modeling and data resources. Overcoming common challenges is essential for successful lifecycle assessment implementation. Let's review some of the most frequent obstacles and practical solutions. 1. Data quality and availability. One of the main challenges is dealing with incomplete, inconsistent, or outdated data from suppliers or internal systems. To address this, prioritize collecting primary data for key processes such as energy and materials. Where gaps remain, use reputable databases like EcoInvent or GaBi. Additionally, establishing supplier engagement programs can improve data sharing and overall data quality. 2. Managing complexity. Modeling complex products, supply chains, or multi-site operations can be overwhelming. Start by building a simplified or screening LCA model and refine it iteratively as more information becomes available. Modular LCA software such as Simapro or openLCA helps break down large systems into manageable parts. Always focus on materiality by prioritizing high-impact stages, commonly referred to as hotspots. 3. Stakeholder alignment and communication. Translating technical LCA results into actionable business insights is another common challenge. Use clear charts and hotspot maps to visualize results, making them accessible to non-experts. Link LCA findings directly to business KPIs, such as cost savings or risk reduction, to demonstrate value. Training teams on LCA basics fosters cross-functional buy-in and ensures that sustainability becomes embedded throughout the organization. 4. Regulatory and methodological changes. Keeping up with evolving standards like EF 3.1, CSRD, or the product environmental footprint can be demanding. Regularly update your LCA models and methods to stay compliant. Monitor regulatory developments and participate in industry forums to stay informed. Finally, use software with up-to-date compliance modules to ensure your assessments meet current requirements. By proactively addressing these challenges, organizations can unlock the full potential of LCA as a driver for sustainability, innovation, and business value. Thank you for your attention throughout this session. As we've seen, life cycle assessment is more than just a technical exercise. It's a strategic tool that empowers companies to drive meaningful environmental and business improvements. By embracing LCA, you position your organization at the forefront of sustainability, ready to meet regulatory demands, stakeholder expectations, and market opportunities. Remember, the journey towards sustainability is ongoing. Keep leveraging robust tools, stay curious, and use your LCA insights to inspire positive change within your business and beyond.